Welcome to Hacking the Pandemic's Most Popular Software, Zoom. When the pandemic forced everybody to work from home, we all bravely installed this software we never heard of before. Everybody had these meetings where children were running around in the background, cats were jumping suddenly in front of the camera, and everybody was saying phrases like, "You're on mute," or "Can you see me now?" Sharing your company's secrets online has never felt more comfortable. I'm Thijs Alkemade. I'm part of the research department at Computest. Computest is a security company in the Netherlands. We mainly focus on pen testing, incident response, code reviews. And together with Daan Keuper, I'm the research department, which is known as Sector 7. And we do research not for our customers, but for the public interest. We are trying to make the world a little bit safer. One of these things is what I'm going to be talking about today. So in April of this year, we demonstrated a zero-day attack against the Zoom client during the Pwn2Own competition. This means that we could take over a remote computer running the latest version of Zoom and the latest version of Windows through the Zoom application. This required no interaction of the user, and we gained full control over that machine as the victim had. Now, we started this research after the targets of this year's Pwn2Own competition were announced. And this year, Zoom was included for the first time because it had gotten so important during the pandemic. This is why CDI, the organizer of the competition, decided to include them this year. So first of all, I'm going to talk a bit about how we approach our research to find these vulnerabilities that we used. Then I'll detail how we exploited them for our full exploit chain. So this is basically our general approach. So first of all, both of us weren't very familiar with Zoom. So the very first step was, of course, to install it and basically look through all of the features it has. Trying to understand what you can send to another user was the main focus, because we knew that this had to be how we started our attack. So we made a list of everything that you can do with Zoom, such as video chats, but there's also the text chat. There's a completely full-featured chat client included if you're logged in, where you can have group chats. We tried to make a list of all of these things. The next step was to look at, well, what does the network traffic look like for the Zoom client? And then specifically trying to match that to the functionalities that we found. So for example, if you send a message, then we see this going over the network. And then we try to understand the architecture of the application a bit more, as much as we could from just having the application. So for example, figuring out what libraries it uses, which open source components might be included, try to identify which library does what functionality, to understand where we might be able to reverse engineer to find where everything is implemented. And then we actually started reverse engineering, but first we had to look for what we wanted to reverse engineer. So that was defining the areas of interest. And then we reverse engineered the relevant parts until we eventually found a vulnerability that we could use. So how did we define those areas of interest? Well, we knew that we had to take over that remote computer. So we knew that for a C++ application, the most likely method would be some form of memory corruption. But something like a buffer overflow is not likely in C++ because you internally have this C standard library using std string, which means that buffer overflows are not as likely as they are in C. And in addition, all of the XML goes through a server because it's based on XMPP. So parsing issues, which is also a great source of buffer overflows, it's also not very likely. And then I had this idea. What if we look at OpenSSL function calls? So Zoom includes a copy of OpenSSL. But OpenSSL is, of course, a C library, which means that every time it needs to call something, it needs to convert from the C++ standard library string objects to C buffers to use that function. And in addition, It is open source and we have the documentation for OpenSSL. This means that it was a very interesting part for us to look at. And pretty early on, I found this in a couple of places actually, which was a good hint that this might be an interesting area to look at. So what you see here is the EVP decode block on the last line. This is the base64 decode function in OpenSSL. And as you may know, if you base64 decode something, then it always becomes smaller, approximately 3/4 of the size of the input. But what you see here is a conversion where a string is allocated or a buffer is allocated. That's not exactly the right size, but instead it is 4 times as large. So there's a shift left for 2 places on the length. This means multiplying by 4. So you see here that these buffer calculations when converting between the C++ string object and the manually allocated buffer are not as precise as they could be. Now this example itself is not really exploitable unless you can somehow trigger an overflow, but that's not likely. But I kept looking for similar types of vulnerabilities. Now, one of the functions Zoom has that not many people know about is called advanced chat encryption. So this is a setting you can only enable if you have a paid account. You must enable it on the website, and it's a pretty obscure checkbox to enable it. And I think not many people use it. And if you look at it together, and actually one other thing important about it is that there are 2 versions of it. So there's a version 1, an older version of the protocol, and there's a version 2. And if you start a new encrypted chat with somebody, then by default you will use version 2. But version 1 is also still implemented. So version 1, if you look at it, then you see that there's a conversion between C and C++, so that OpenSSL interaction. It also uses the OpenSSL API, which means we have documentation, and there's a hidden, it's not a well-known feature, and it's also an older version of the protocol. So if you look at all of that together, if you combine that, and this just means that as a security researcher, I think this is very interesting code for me to reverse engineer because there's just a very high probability of vulnerabilities. So how did we look at this? So I looked at the places where an OpenSSL function was being called and tried to look where the buffers for those calls were being allocated, trying to trace that back, all of the places where that function was called. And then I tried to guess what the contents of the buffer may be in order to determine whether it's input from another user. For example, if it's something local, like from a file, then the vulnerability is not as likely as if it's received from another user. I also tried to guess at what kind of encryption protocol they might have implemented for this advanced chat encryption. And then eventually I find a vulnerability that we could use. So to describe that, I have to tell a little bit about how you start this encrypted chat. So if you start a new encrypted chat, then you send a message which is encrypted. It's encrypted using some symmetric key. And I will call that a message key. This key has a specific identifier. I call it a key ID. And whenever you send a message, the receiver will see that it is encrypted with a key it doesn't know. It doesn't recognize the key identifier. So it requests the key from the sender, and it includes a X509 certificate, which we'll call an identity key. And then the sender of the message will reply to that request with a response key message. And this response key message contains a message key, which is encrypted and then signed using the identity key of both the sender and the receiver. So encrypted using the receivers and signed using the sender's keys. Now, even this version 1 of the protocol had 2 different options. There's one using RSA keys, and there's one using elliptic curve cryptography. And because elliptic curves don't generally have an operation like encrypt. They implemented this using elliptic curve Diffie-Hellman combined with AES. So they derive a secret from the elliptic curve Diffie-Hellman and then use that for AES. And in this implementation, they decrypted something, the message key, and they allocated a 1024 byte buffer for this message key. And when using RSA, they properly checked whether it would fit in that buffer. But when when they used the elliptic curve variant, there was no check on the size of the ciphertext and therefore on the decrypted result. So if you send a response key message with a ciphertext of more than 1024 bytes, then this would trigger a buffer overflow because it would write data out of bounds. So there's a couple of nice properties of this buffer overflow. So first of all, it's arbitrarily large. We can overwrite as much data as we want. Practically, there may be some limit based on the packet size that you can send over XMPP, but that's way more than we needed. There's also no restrictions on the character set. It doesn't need to be printable or ASCII or something like that because it's decrypted. It can be anything. And the nice thing for the contest here is that we could trigger it using just chat messages without any interaction of the victim. We only needed to be an accepted contact. So they needed to accept their contact request. And from then on, it would be completely automatic without any user interaction. But there are also some challenges with this buffer overflow. So first of all, the allocation that we do overflow has a fixed size of 1040, so that 1024 has some overhead. In addition, the overflow size must be a multiple of 16, which is the block size of that AES, of the AES cipher. And then the most challenging part here is that this buffer is allocated and then triggers the buffer overflow when handling just one message over XMPP. So what this means is that we cannot first place the buffer and then place something after it and then trigger the overflow. We have to make sure that whatever we want to overwrite is already there in memory. And this is really where most of our challenges with writing the exploit were. So as the tweet said, there were 3 vulnerabilities in total. There were 2 additional vulnerabilities we had to use. And these by themselves are lower impact than the buffer overflow we just found. So first of all, because it's a heap buffer overflow, we have to manipulate the contents of the heap to use our exploit. And through the chat, manipulating the heap proved to be quite difficult because we had we didn't have very precise control. So we wanted a way to be able to more directly create allocations. So one way we used for that was to set up a HTTPS connection to a server we control. And this also proved to be very helpful for having a channel for the information leak. So by combining 2 packets in a very unexpected way, we found a way to set up an HTTPS connection to a server under our control. And the second vulnerability, even lower impact by itself. At some point, we needed to fill up the memory of the remote Zoom client with specific data that we specified. But one thing we found is that if you send an image to somebody, then it's downloaded if it's under a specific size. However, if you send a Giphy link, so a GIF file from the Giphy service, then it's always downloaded regardless of the size. So what we did was a trick where we sent a link to a GIF file that we uploaded, but as if it was a Giphy file using path traversal, and then the file was downloaded regardless of the size and then loaded into memory. I'll talk about why we needed this later. So now for the exploit. So just to clarify, it took us about a week and a half to find this buffer overflow. after starting our research. But then turning this into an exploit that we could use during the contest, that took us a month and a half more. And it wasn't that reliable in the end, but I'll talk more about that later. So the steps for this heap exploit were, first of all, grooming the heap into a predictable structure that we could then exploit. The heap in Windows works like this. So there's a list of all of the blocks that are currently free, and they are sorted by size, and it's a linked list. So when a new allocation request comes in, and it traverses that list until it finds one that is larger than the request, then it returns that to the application. And when a block is freed, then it is put back into the in that linked list. But first it checks if it can combine it with the block in front of it or after it. Now, we tried for a while to write our exploit using this heap, but it was proving to be quite challenging. Now, the way this works in the Windows is that if you have 17 active allocations for a specific size, then the heap implementation that will be used is the low fragmented heap instead. So this is used to make sure that certain common sizes, like the powers of 2 or multiples or numbers that are objects that are quite common within the application, those are grouped together to make the fragmentation of the memory less. So on this free list, writing our exploit it wasn't working very well. So eventually we decided to focus on a low fragment heap. Now how this works is that similar sizes are grouped together within a bucket. So this means that there's a specific range and all objects within that size are handled in one specific bucket. And when a new allocation is made, a random free chunk from that bucket is returned to the application. This means that precisely grooming a heap for a heap exploit is impossible because there's always this randomization that you need to deal with. You cannot control exactly what will be after our block in memory. So one thing we could do is to try to make sure that we could somehow control this randomness. And for that, we used something which we have the following video to demonstrate. So we could fill up the memory by sending new messages to the user, but we could also delete those messages again, revoking the message, I think Zoom calls it. So the trick that we use is that we would send a lot of messages to fill up the bucket. And this would make sure that existing objects, so the objects in orange here, would not get overwritten because they are in the first bucket. And then we would send so many messages that we would eventually end up in the bucket 3 here. Now, because bucket 3 is the last one where a new allocation was made, all new allocations will be made from that bucket. So in this case, you have a lot of room. There's a lot of free space within this bucket, but there's also no dangerous objects here, so no orange objects. So this way we could make sure that we would not overwrite something dangerous, something already existing. And then we could just keep retrying and retrying our exploit until it would eventually work. So this is the way we try to groom the heap into a shape where we could use our exploit. Now, next step is to have an information leak. This is needed because in Windows, just like in many operating systems, there's a defense mechanism known as address space layout randomization, or ASLR. This means that all of the libraries and all of the other data of the application are loaded at random locations in the memory. This means that if you want to build an exploit, then quite often you first need to figure out where these libraries are in memory, because only then you can refer to them. Now for our exploit chain, we wanted to leak an address from libcrypto. This is one of the OpenSSL libraries. I'll talk about why we needed one from this particular library later. And if we wanted to use a buffer overflow for this, we knew that it had to be within the same bucket as the buffer overflow that we found. Because if the information leak uses an object of another size, it will be in a different bucket, and then we cannot reach it. But we also had to think about how are we going to receive that information back to us? So because it's an XMPP connection, this always uses XML. So if you include some binary data in this, then it will not be valid XML and it will not go through the server, so it will not reach us. Eventually found the following object, a TLS1 underscore PRF underscore PKey underscore context. This is an object that's created by OpenSSL if you set up a new TLS connection, or TLS 1.0 up to 1.2. But just like the buffer overflow, it's very short-lived. So it's created, it's used, and then deallocated during one packet of the handshake, which is actually used for checking the integrity of the handshake, comparing that it was the same on both sides. And we found that it is within our bucket, and it contains a pointer that we were interested in at the first slot. But of course it was deallocated, but it doesn't actually clear that pointer from the first slot if the object is freed. So here's the struct definition of this object. As you can see here, the first one is a pointer. In this case, it's a pointer to a struct that implements a hashing function. Now, when this object is freed, then it clears a seed because that's sensitive data, but doesn't clear the other fields. So even in a freed object, there's one pointer that you can use to use your information leak at the first slot. So we formulated the following plan. We used that first HTTPS connection to set up two connections to a server that we control. On the first connection, we close the connection after the handshake. This will ensure that these objects from OpenSSL are in memory, although deallocated. On the second connection, we request a URL of 1025 bytes, or just something within the size range of our bucket. And then we use the heap overflow, the buffer overflow, to overwrite the null byte in memory after the path. Then we complete the connection, and this will ensure that the memory behind the request string is sent to us. And then we try to do this in such a way that the deallocated object is actually behind the path. And then by overwriting the null byte, when the request is completed, it sends the path with the deallocated object after it to us. And therefore it reveals the address from libcrypto that we wanted to leak. So this took quite a while for this to work for the first time. So as you can imagine, it required 3 different objects to be in place after another. So there's first the buffer overflow, then there's the request path, and then there's a deallocated object after it. And all of this with the heap randomization that we had to deal with. So the first time it worked, it took about, I think, 3 days of trying to get this to work. And then it didn't work again for another couple of days. And we had to reduce that to at most 3 minutes for the competition. Therefore, we had to do some checks to make this make the chance bigger for this to work. The first one is to set up multiple connections to both web servers. So there's more paths in memory that we could override, and also more of those OpenSSL objects. And we also noticed that instead of closing the connection immediately after the handshake, you could also renegotiate the connection. So renegotiating is a feature in OpenSSL or in TLS, that you can use to basically do another handshake on an existing connection. And OpenSSL considers it fine if you just keep doing this in a loop instead of actually doing something with the connection. So by constantly renegotiating that connection, the bucket kept being filled up with those TLS PRFP key context objects. Even though they were deallocated, there were a lot of them. And you could also trigger the overflow multiple times after each other to increase the chance that you would overwrite the right thing. So normally you can increase the chance of a buffer overflow by just creating more objects. Just create a lot of objects and then try to overflow all of them, or create more objects that you want to overwrite on and try just once. But for us, we really needed a very careful balance, because one of the objects that we needed was actually deallocated space. So if we increase the number of connections by too much, then there would no longer be any of those deallocated space available to leak the information from. So we spent quite a few days trying to tweak the exact parameters that we used for this information leak to get it reliable and fast enough for the competition. But this still remains one of the most unreliable steps of the exploit. The next step, we knew where the library was in memory. The next step was to actually take control of the control flow. So this means executing something else, not yet code that we have specified, but just executing something else in memory that was already in the code. So for this, we had to find something like a function pointer or a vtable. And then we had to override it and then make sure that it was also being called. And in this case, also for the buffer overflow, we had to find something that was in the size range of our bucket. So we were looking for an object within this 1025 to 1088 bytes, which contains a vtable. But a vtable is actually an indirection step. So if you override a function pointer, then you can directly write some contents that you want to write, or a different function that you want to call. But the vtable actually has to be pointing to the actual function pointers. So we not only have to overwrite that vtable, we also have to make sure that that vtable is somewhere within memory. And then also we have to make sure that this vtable was used. And this is where we use that second additional vulnerability, that Giphy vulnerability. Now, we used the Giphy file upload to upload an image containing our fake vtable. And because Zoom was a 32-bit application on the Windows, this means that there's 2 GB of RAM available for the process. And if we send the same link multiple times, it's downloaded only once, but it is loaded at separately into memory. So what we could do is just upload a 25 MB image, send the same link 20 times, and then a large part of the memory of Zoom would be taken up by the data that we specified. And at that point, we could reliably guess that specific address would be within that GIF file. And there we could place our vtable that we would then use. Now, to find the object that we could overwrite, we also had to find an object that we could overwrite with a vtable that would actually get used. And for that, we found the following sound. This is the ringtone you hear when somebody is calling you through Zoom. Now, the way this works internally is that Zoom includes a version of WebRTC, pretty old version. And whenever this sound is being played, it creates what's known as a file wrapper object from WebRTC. And every loop of this sound, it I think it opens the file, reads the content, and then closes the file again. So each iteration of the sound, it creates a new file wrapper object. This file wrapper object neatly fits within our bucket. And the vtable of this object actually contains that close function for when the sound is finished. Now, this is great for us because it means that these objects are created quite often when somebody is being called, and it has a vtable that's actually being used. So if we start ringing somebody, and they don't even need to answer it, and we then trigger the buffer overflow, then we could override that vtable pointer, which means that when the close function is being called, it then would call something else that we can specify. In this case, we could be a little bit more aggressive than for the information leak buffer overflow because, well, we're almost there. So we could overflow a lot or just try to overflow very often. We didn't need to be as careful as we were during the information leak. Now, the next step, or actually the final step, is to actually execute our own code. And for that, we had to deal with a relatively new mitigation in Windows, or a technique that's used for defending against vulnerabilities like this. And this is control flow guard. This is used to prevent against return-oriented programming. What this means is that whenever a function pointer or a function from a vtable is being called, then it at runtime checks if that address that it is about to call actually is a valid start address of a function. So if it's something else, somewhere within the middle of a function or very near the end, then it will refuse to call it and crash the application. This means that you can only call a complete function from a function pointer or a vtable. Now, we had two ideas of getting around this. First of all, we looked at if you could maybe call just existing functions that you could use. For example, loading a new malicious library from disk. But we didn't really get this to work. But the second option was to find a library that doesn't use control flow guard. So control flow guard has to be enabled at compile time. And we noticed that libcrypto in Zoom doesn't have control flow guard enabled. It actually, at the time, was not yet possible to compile OpenSSL with control flow guard on the Windows. And not having control flow guard actually means two different things. First of all of the dynamic function calls, so calling a function pointer in that library, is always allowed because there's no check inserted. But also, more importantly for us, whenever something else tries to call an address that falls within libcrypto, then this is also always allowed. This is because the metadata for knowing where a valid function start address is not present for this library. So this means that it just always allows it. This means that we could just, if we used return-oriented programming with only gadgets from libcrypto, then we would not have an issue with control flow guard. So how we combined our blockchain was as follows. First of all, we used the stack pivot gadget from libcrypto. This means that we could replace the stack with something we specified, which means that we could then initiate a ROP chain. These were just some misaligned instructions that we could use to override the stack pointer to point to something within the data we overflowed. And then we used return-oriented programming to mark some part of our GIF file as executable. So normally data is not executable in the Windows. This is known as DEP, data execution prevention. But by using the specific function calls, we could make this executable and then jump to it. Of course, we only had the gadgets from libcrypto that we could use. And then we could jump to some shell code that we had written, which would launch calculator or something like that, start reverse shell back to us. Now, during the competition, first, before the competition, we had tested it a couple of times and we thought that it had about a 50–60% reliability. This is not great, but during the competition, you actually get 3 attempts. So we thought that this would be good enough to try this with. Now, if you watch the stream, then you may have seen that the first attempt failed, and then resetting it took a while. So what they had to do at that point is to actually clear all of the chat messages in the Zoom client, because that might influence the layout of the heap. But for some reason, this took quite a long time. And this means that it was looking very unlikely that we could even do a third attempt. Because how it works is that you get 20 minutes. Within that 20 minutes, you have 3 attempts, and each attempt can only take 5 minutes. And because the timer was already below 10 minutes, it wasn't likely that a third attempt would have any chance of succeeding. But then, with just 20 seconds left on the clock, that second attempt did succeed. And we had a reverse shell and demonstrated that we had taken control of that computer. And then we had a call with Zoom to disclose the vulnerabilities that we found, as is usual for this competition. And they informed us that of these 3 vulnerabilities, they didn't know any of them, which means that we got the full reward and the Master of Pwn title. Zoom applied a server-side fix quite quickly, because all of these chat messages have to go to the server. They could quite easily check if there were any attempts to use this exploit by looking at if there are any encrypted messages with too much payload. And they fixed it in a release pretty soon after. And if you have not updated since then, so more than half a year, then really make sure that you update so you have that latest patch. So they gave us permission to write a fully detailed write-up of this. And if you want to read it, then you can visit this link or scan this QR code. Thank you for your attention. If you have any questions, please feel free to reach out.